Hello everyone, I'm Carlos and today we're going to be talking about silicon photonics. What are they and what is their role in modern energy efficient data centers? We'll explore their recent technological advancements, their bottlenecks, and their environmental and economical implications. We're going to be talking about where silicon photonics has improved and where it might be going. So what are silicon photonics? Silicon photonics is arguably an emerging technology, only having been around the past 40 years or so. They leverage the unique properties of silicon to address the demand for high bandwidth, energy efficient systems. Instead of using electrical signals and copper interconnects like CMOS does, these may be limited by power and bandwidth constraints, so in place of that, silicon photonics uses light to transmit data. Doing this significantly reduces power consumption while enabling much faster data transfer rates through methods such as WDM. The technology has evolved significantly, starting with small-scale integration for basic optical communication systems and advancing to large-scale integration that supports thousands of optical components on a single chip. These advancements allow silicon photonics to address critical bottlenecks in applications such as data centers, sensing, and quantum computing. In this presentation, we'll explore the challenges silicon photonics faces, the innovations that are driving the field forward, and its impact on the economy and the environment. By the end, you'll see why this technology is ready to redefine the future of high-speed, low-power systems. Let's start with the challenges. Integration remains one of the toughest problems in silicon photonics. While silicon is an excellent material for guiding light, it's not naturally equipped to handle optical gain, which is why integrating components like lasers and amplifiers is so difficult. These elements often require materials like indium phosphide or gallium arsenide, which are not compatible with standard CMOS processes. Fabrication challenges further complicate the picture. For instance, waveguides need to be aligned with nanometer level precision to minimize losses and crosstalk. Even minor misalignments can lead to degraded performance and scalability issues. Another critical task is light modulation, where plasma dispersion-based modulators dominate. While they offer good bandwidth, they suffer from trade-offs between efficiency and insertion loss, limiting their overall effectiveness in large-scale systems. Coupling light into and out of photonic devices is another major bottleneck. Techniques like grating couplers are widely used, but they introduce polarization sensitivity and significant insertion losses, which reduce system efficiency. Finally, packaging is a major pain point. Achieving precise optical alignment at scale is extremely challenging and adds substantial costs. Thermal management is another issue, especially as photonic circuits become more densely integrated. Without effective heat dissipation, performance can deteriorate over time. These challenges collectively underscore the technical barriers that must be overcome for silicon photonics to scale effectively. Despite these challenges, we've seen remarkable progress in the field. Large-scale integration has been a game changer, enabling thousands of optical and electronic components to coexist on a single photonic integrated circuit. Advances in waveguide design and the miniaturization of modulators have been key to achieving this density. Hybrid integration has also addressed one of the biggest challenges, integrating efficient light sources. By combining 3-5 materials like indium phosphide with silicon, we can incorporate lasers and amplifiers directly onto silicon chips. This approach is already being adopted in commercial applications. Beyond hybrid approaches, heterogeneous integration techniques such as wafer-to-wafer bonding and photonic wire bonding are opening up new possibilities for scaling photonic devices. These methods improve alignment and reduce optical losses, making them ideal for high-performance systems. Emerging materials are another area of innovation. Thin-film lithium niobate and barium titanate, for example, are enabling modulators with much higher bandwidth and lower power consumption compared to traditional plasma dispersion-based devices. These materials also exhibit lower optical losses, making them attractive for next-generation photonic systems. Process design kits, or PDKs, are evolving rapidly as well. Using inverse design techniques, these kits allow designers to optimize components before fabrication, ensuring predictable performance and reducing development cycles. These advancements collectively address many of the challenges we discussed earlier, paving the way for silicon photonics to scale further. Now, let's talk about the economic side of silicon photonics. One of the key drivers for its adoption is the cost reduction enabled by economies of scale. As more companies adopt silicon photonics, manufacturing costs are decreasing, making it more accessible to smaller organizations. Foundry level standardization is playing a major role here. Many foundries now support multi-project wafer runs where multiple designs share a single wafer. This approach not only reduces costs, but also encourages innovation by lowering the barrier to entry for startups and research groups. The economic potential of silicon photonics extends well beyond data centers, where it's already a dominant technology. It's also making inroads into applications like quantum computing, automotive LiDAR, and biosensing. These markets add further value to the ecosystem and improve the return on investment for companies adopting this technology. However, there are still hurdles to overcome. Achieving cost parity with traditional copper interconnects remains a challenge, especially for lower volume applications. Continued innovation in manufacturing and integration will be critical to closing this gap and ensuring widespread adoption. Let us now shift to the environmental impact of silicon photonics. One of its most significant benefits is energy efficiency, particularly in data centers. Optical interconnects consume far less power than copper-based systems, which translates to enormous energy savings when scaled across thousands of servers. Another advantage is the reduced material footprint. By integrating optical and electronic components onto a single chip, silicon photonics eliminates the need for many external components, reducing the overall research requirements for high bandwidth systems. However, we also need to consider the environmental challenges. The disposal and recycling of photonic devices are complex due to the wide range of materials used. Developing sustainable methods for recycling these devices will be critical as adoption grows. Even with these challenges, the energy efficiency gains and reduced material use make silicon photonics a cornerstone technology for greener, more sustainable systems. To summarize, silicon photonics is a technology that addresses some of the most critical bottlenecks in modern systems, including integration, modulation efficiency, and packaging. Innovations like hybrid integration, advanced materials, and process design kits are driving the field forward, making large-scale systems possible. Economically, silicon photonics is benefiting from economies of scale and expanding into new markets from data centers to automotive and quantum technologies. Environmentally, its potential to reduce energy consumption and material use positions it as a key enabler of sustainable technology. While challenges remain, such as cost parity and sustainable recycling, the progress we've seen so far demonstrates the enormous potential of this technology. Silicon photonics isn't just a promising field, it's already reshaping industries and paving the way for a faster, more efficient, and more sustainable future. Thank you for listening.